In this video, we're going to learn how to calculate areas of regions that are not bounded by the x-axis. So we can think back to geometry. If we were finding the area of some unknown region, say this blue piece here. If we knew the area of the yellow, we can take this whole area and we can then subtract this piece that we don't need. And so that's what we're doing here. And that leaves us the area of the region that's in the middle. So when we're calculating area between f and g, we need to find the area under f, which is going to be done by integrating f. Then we're going to find the area under g, and if we subtract the two, that gives us the area between two curves. We've been doing this all along, except our lower boundary has been the x-axis. So if I were to calculate, let's say, the area of this region, I could take the area of the function and subtract the area of this horizontal line, which is y equals 0. So if I were to integrate f of x minus 0, you can see this is the same as just integrating f of x. So that's why we haven't really seen anything here, because it's been a 0, and that means that the x-axis is one of our boundaries. So if we come down here, this is just written a little bit more formally. The key thing here is when we're integrating, we need to take the larger value minus the smaller. And that gives us the distance between the two functions. And so to give you a visual, just remember when we're integrating, we're kind of splitting this up into really, really thin rectangles. And I need to find the length of that line. And so the length is going to be whatever this value is on top minus the value on the bottom. So that's going to be my higher function minus my lower function. And when I integrate, it's going to allow me to add all of these together. And you can see eventually it gives me the area of that shaded region. So I apologize in this example. I know you don't have any space, so you can write this out to the right or on a separate sheet of paper. A rough sketch can really help with this. So we can see that this is a quadratic and its y-intercept is 2. So it does open upward, so it's going to look kind of like that. And y equals negative x is linear with a negative slope. So if it just said, find the area of the region between these two curves, do you kind of see how maybe there's an infinite amount of space between these two, and it just keeps going on and on and on forever. So that's why they give me some other conditions. X equals 1 is a vertical line that goes right here. And x equals 0 is a vertical line here. So they're asking us to find the area of the region bounded by those 4 lines. So that's going to be this area right in here. And the way we're going to calculate that is we're going to find the distance of one of these very, very thin rectangles. So that's going to be my quadratic equation minus my linear, or top minus bottom. So I'm going to have x squared plus 2 minus a negative x. And this gives me the distance, or the height, of one of those very thin rectangles. And remember, we calculate area by height times width, or length times width. So out here, this dx gives me that really, really thin width. And then by integrating, I'm going to add them all together. And my very, very first rectangle is going to be here at 0. And I'm going to add these all together until I get to 1. And so if I calculate this, it will give me the area between those two regions. Just remember when we integrate, and we're not going to integrate everything in this video just to save time, but I'm just going to apply the power rule. So I get x to the third. Here I'll have 2x. Remember, we can simplify this to plus x so that we get plus 1/2 x squared. And then I'm going to apply the fundamental theorem of calculus from 0 to 1. If I plug in 1, we get 1/3 plus 2 plus 1/2, and that's all going to be minus 0. So technically, that's my answer. So sometimes they actually don't give us specific values because the areas actually are explicitly bounded. So to give you an idea of what I'm talking about, if you were to graph this, this is a quadratic equation that opens downward and has a y-intercept of 2. So he's going to open downward. And this is a linear function that's increasing. So you can kind of see my area naturally has a boundary because my functions cross. Since they didn't give me those, like they did here in the last example, I have to find those values. And so the way we find these 2 points is we set these functions equal to one another. So I'm going to say, what if 2 minus x squared was equal to x? So if I take this guy to the other side, I get negative x squared minus x plus 2. And if I were to factor this, I can go ahead and change the sign of each of these. And I see that this factors to x plus 2, x minus 1. And so solving then, I see that they cross at negative 2 and positive 1. So this boundary here is negative 2, and this is 1. So now to set up the integral, again, we're not going to finish this, but to set up the integral, I need to calculate the distance of one of my really thin rectangles, and then I'm just going to add them together. So the distance of one of these is going to be a point on the quadratic equation minus a point on the linear equation. So that's going to be quadratic minus linear, or 2 minus x squared minus x. This is going to add them all together, and this multiplies them by that really, really thin width. And my very first one starts here at negative 2, and I'm going to add these together all the way till I get to 1. So negative 2 to 1 is how I'm going to add those together. And this is what we would calculate to find the area of that region. Okay, our last example here, and you won't know this graph, I just have this graph here just to help you see what's going on. But you can see that we actually have 2 regions. We have this region plus this region. So think back to geometry. When I'm calculating area of 2 regions, I find the area of one, and I add it to the area of the other. We do have to set up 2 integrals here, because remember, the way we calculate is we find the height of one of these very thin rectangles, and we always take the upper function minus our lower. And in this case, for this region, it's going to be the cubic minus the quadratic. But over here you can see now the quadratic function is the one that's on top. So we're going to calculate the heights of those rectangles differently. Again, we would normally need to see where they cross, and we won't have this graph. So if we set these equal, we get 3x cubed minus x squared minus 10x equals 2x minus x squared. If I add x squared and subtract 2x, that gives me 3x cubed, those cancel, minus 12x equals 0. If I factor out of 3x, I see that x squared minus 4 is my second factor. And if I solve this, I see that I have solutions of 0 and plus or minus 2. So that's how we can calculate by hand where these cross. And then if you want, you can draw yourself a sketch. You can always make a table of values to give yourself a nice rough sketch. So in order to calculate this then, again, I'm splitting this up into very, very thin rectangles. And so the height of one of these rectangles is going to be my cubic minus my quadratic. And in this particular case, I'm going to use function notation because these guys have names. So I'm going to take my cubic function minus my quadratic. And those are the heights of the rectangles from negative 2 all the way to 0. And so once I'm done calculating that, then I can add it to the area of the second region. And the second region says take the quadratic minus the cubic. So the quadratic is g of x minus f of x. And those rectangles start here at 0. And we're going to add them all the way here until we get to x equals 2. And if I were to go ahead and calculate each of these, that will give me the area of the total region between the 2 curves. And we're going to stop there for this video.